It might mess with your head a little to realize this, but we are, in fact, living in an ice age right now. Seriously, it started about 2.6 million years ago, and technically, it hasn't ended. And here's the really wild part. Every 100,000 years, like clockwork, our planet undergoes this insane transformation, with massive ice sheets covering huge areas of the continents before melting away again. So, in this video, I want to break down this 100,000-year cycle, how it works, why it happens, and what kind of world it creates during the cold phases, as well as what happens when it shifts back to warm. You're going to meet the creatures that thrived in Ice Age conditions, learn how humans survived and adapted, and understand why it all came crashing down so recently. And at the end, I want to talk about where we are in the cycle right now and what that might mean for our future. Let's start with the basics. An ice age isn't just a cold period. It's an extended chunk of time, millions of years, where Earth's temperature drops enough that massive ice sheets and glaciers take over large portions of the planet's surface. And we're currently in one, the Pleistocene Ice Age, which kicked off about 2.6 million years ago and technically hasn't ended yet. Now, within any ice age, you get fluctuations. There are glacial periods where it's really frozen and interglacial periods where it warms up. We're in an interglacial period right now and have been for about 11,700 years. So, when people say the Ice Age, they usually mean the last glacial period, which lasted from about 115,000 years ago to 11,700 years ago. That's when the ice sheets were at their biggest and the megafauna were running the show. During that last glacial period, the temperature was only about 6 degrees Celsius colder than today on average. 6 degrees doesn't sound like much, right? But we're not talking about 6 degrees in one spot. We're talking about 6 degrees worth of thermal energy being sucked out of the entire planet, all the oceans, all the land masses, the whole atmosphere. That's enough to completely transform the world. Huge ice sheets covered most of Canada and northern Europe. The Laurentide ice sheet in North America and the Fennoscandian ice sheet in Europe were kilometers thick in some places because so much water was locked up in ice. Sea levels dropped by over 100 meters. You could walk from England to France. You could stroll from Asia to Alaska across what's now the Bering Strait. The coastlines were completely different, and the landscape was mostly tundra and cold grasslands, dry and windswept, nothing like the forests we see today. So what caused this? Why does Earth go through these dramatic swings every 100,000 years? The answer starts with this Serbian scientist named Milutin Milankovitch. Back in the early 1900s, this guy figured out something nobody else had really considered. What if ice ages weren't caused by anything happening on Earth, but by changes in Earth's position relative to the Sun? See, Earth's orbit isn't perfectly circular. It's slightly elliptical, and the shape of that ellipse changes over time because of gravitational pulls from other planets, mainly Jupiter and Saturn. Sometimes our orbit is more circular, sometimes it's more stretched out. And this cycle of changing from circular to elliptical and back takes about 100,000 years. That's the first Milankovitch cycle, called eccentricity. When Earth's orbit is highly elliptical, the distance between Earth and the Sun varies more dramatically throughout the year. This affects how much solar radiation hits different parts of the planet at different times. And here's the crucial part. It's not about how much total sunlight Earth gets. It's about where and when that sunlight hits. Northern Hemisphere summers are the key because that's where most of the land is. If Northern Hemisphere summers are cool enough that winter snow doesn't fully melt, the snow sticks around. Year after year, it piles up. Eventually, you've got ice sheets forming. And once ice sheets start growing, they reflect more sunlight back into space, which cools things down even more, which allows more ice to form. It's a runaway feedback loop, but eccentricity isn't the only cycle. There's also obliquity, which is the tilt of Earth's axis. The more tilted Earth is, the more extreme the seasons. This tilt varies on a roughly 41,000-year cycle. When Earth is less tilted, the difference between summer and winter is milder, which means summer might not be warm enough to melt all the winter ice. Ice accumulates, ice age begins. The third cycle is precession or wobble. Earth wobbles on its axis. I find myself fascinated by the way our planet wobbles. It's like a spinning top that's starting to slow, and this wobble changes which hemisphere tilted toward the sun during different parts of Earth's orbit. This happens on a 26,000-year cycle, affecting the contrast between the seasons. Right now, the Northern Hemisphere experiences winter when Earth is closest to the sun, making our winters milder than they could be. But during other parts of this precession cycle, that flips, and our winters can become much colder. When you combine these three cycles, eccentricity, obliquity, and precession, they work together to control Earth's long-term climate. What's strange is that the 100,000-year eccentricity cycle is actually the weakest of the three in terms of how much it changes incoming solar radiation. The other two cycles should matter more, but when scientists started drilling cores out of ocean sediments and ice sheets to reconstruct past climates, they found that the dominant pattern is 100,000 years. This weak cycle somehow dominates the whole system. It's called the 100,000-year problem, and scientists are still trying to fully explain it. The leading idea suggests there are feedback mechanisms that amplify the eccentricity cycle. Perhaps it takes a long time to build up ice sheets, but they can collapse relatively quickly. The system spends most of its time slowly building ice during the cool phases, then rapidly melts when conditions shift to warming. This asymmetry could explain why the 100,000-year pattern shows up so strongly. What we know is that for the past million years or so, Earth has been going through these 100,000-year climate cycles. A slow buildup of ice over tens of thousands of years, then relatively rapid melting, followed by another slow buildup. During these cold phases, the world became a stage for some of the most incredible animals ever to walk the planet, the megafauna. And the word mega is no exaggeration. Some of these creatures weighed 4,500 kilograms or more. There are theories about why everything got so big during the ice ages. One idea is Bergmann's rule, which suggests that in cold climates, mammals tend to be larger because a bigger body has a lower surface area to volume ratio, meaning less heat loss. This is why polar bears are bigger than other bear species, and why Ice Age mammals tended toward the gigantic. But size alone doesn't tell the whole story. These animals had incredible adaptations for surviving in a frozen world. The most famous of these, The poster child of the Ice Age is the woolly mammoth. Woolly mammoths weren't actually as huge as you might think. They were about the same size as modern elephants, maybe a bit shorter, but they were built completely differently. They had thick, shaggy fur with two layers, a dense underwool and longer outer guard hairs. This coat could be up to a meter long in places and provided insulation so good that mammoths could handle temperatures of 40 degrees or colder. They also had small ears to minimize heat loss, unlike modern elephants with their big floppy ears used for cooling off. And they had a layer of fat up to 9 centimeters thick for extra insulation and energy storage. Their skulls were specially shaped too, with large sinus cavities that helped warm and humidify the cold, dry air before it reached their lungs. Breathing in super cold air can damage your lungs, so this was a crucial adaptation. Their teeth were perfect for grinding the tough grasses and sedges that grew on the mammoth steppe, this unique cold grassland ecosystem that covered huge areas during glacial periods. As their teeth wore down, new ones would move forward from the back of the jaw. A mammoth would go through 6 sets of teeth in its lifetime. We know so much about mammoths because some have been found frozen in permafrost, almost perfectly preserved with fur, skin, and even stomach contents intact. Scientists have studied what they ate, extracted their DNA, and found that they had special hemoglobin variants that worked better in the cold, allowing their blood to deliver oxygen more efficiently in freezing temperatures. These animals were fine-tuned for Ice Age conditions. But mammoths weren't alone. The Ice Age world was packed with megafauna. Woolly rhinoceroses roamed the same landscapes, covered in thick fur with massive horns that could reach over a meter long. They used these horns to plow through snow to reach vegetation underneath. Giant ground sloths lived in the Americas, and these weren't the cute little tree sloths we know today. Some species weighed several tons and could stand up to 4 meters tall on their hind legs. They were too big to climb trees, so they lived on the ground, feeding on vegetation and incredibly digging burrows. We found their burrows, tunnels up to 40 meters long, with claw marks on the walls that matched their fossilized claws perfectly. There were glyptodonts, basically car-sized armadillos with shells made of fused bone plates. They couldn't roll up like modern armadillos, but they didn't need to. Their shells were tough enough to stop most predators, and some species had club-like tails covered in bony spikes that they could swing as weapons. Recent studies suggest they might have been able to rear up on their hind legs, which means you could have had these armored tanks standing upright and swinging spiked clubs. That's both awesome and terrifying. And then there were the predators. Saber-toothed cats prowled the Americas with canine teeth up to 18 centimeters long, curved like daggers. They used these to deliver killing bites to the throat or belly of prey, causing massive bleeding. Cave lions in Europe and Asia were larger than modern lions. Giant short-faced bears in North America might have been the largest mammalian land predators ever, standing over 3 meters tall on their hind legs. Dire wolves hunted in packs and had more powerful jaws. I keep thinking about a frozen planet inhabited by giants. It's a world sculpted by a 100,000-year cycle, a world where ice sheets relentlessly grow and melt, where megafauna thrive and then struggle, For hundreds of thousands of years, this cycle repeated, an endless rhythm of ice and thaw. But then, about 11,700 years ago, something shifted. The ice melted as it always had, but this time, the megafauna didn't recover. Within a few thousand years, they vanished, and we're still grappling with why this cycle failed them. Was the warming too rapid? Did humans, evolving and spreading through these cycles, finally possess the tools and numbers to hunt them to extinction? Or was it a blend of both? Let's journey back to the last glacial maximum, roughly 20,000 years ago. The 100,000-year cycle was at its coldest, ice sheets at their peak. The world was unrecognizable. Imagine ice sheets blanketing all of Canada, reaching into the northern United States, in some places 3 kilometers thick. That's like stacking the Burj Khalifa, the world's tallest building, more than 3 times over, but instead of steel and glass, it's solid ice covering a continent-sized area. The sheer weight of that ice pressed down on the Earth's crust, deforming the very rock beneath. Europe had its own massive ice sheet, the Fennoscandian, covering Scandinavia, the Baltic, parts of Britain, and northern Russia. In total, we're talking about maybe 15 million cubic kilometers of ice sitting on land. If you spread that evenly across the Earth's land surface, it would be about 100 meters deep everywhere, an almost incomprehensible amount of frozen water. With so much water locked up, sea levels plummeted by 120 meters, the height of a 40-story building. Coastlines extended far beyond where they are now. The English Channel vanished, Britain connected to mainland Europe by dry land. The Persian Gulf became a river valley. Indonesia, now thousands of islands, was a single landmass connected to mainland Asia. Australia, New Guinea, and Tasmania formed one giant continent. And between Alaska and Siberia, where the Bering Strait lies today, stretched a vast grassy plain called Beringia. The world map was utterly transformed. But it wasn't just coastlines that changed. The climate was radically different. Colder, yes, but also much drier. With so much water trapped in ice and colder ocean temperatures reducing evaporation, the atmosphere held less moisture. Deserts expanded, rainforests shrank. The Amazon basin was drier, a mix of grassland and scattered trees. The Sahara grew even larger. Much of the world was covered in tundra or steppe, cold, dry grasslands with few trees. The ice sheets acted like giant refrigerators, generating cold, dense air that flowed off in powerful winds. These winds picked up dust and silt, carrying it hundreds or thousands of kilometers. Some parts of China have dust deposits over 100 meters thick from glacial periods. The dust storms must have been incredible, blotting out the sun for days. This was peak glaciation, harsh, cold, dry, and windswept. Yet life didn't just survive, it thrived. The megafauna weren't barely scraping by. They dominated these ecosystems, their numbers perhaps matching or exceeding the density of large animals in Africa today. The mammoth steppe was the dominant ecosystem across vast stretches of the Northern Hemisphere, a type of grassland that no longer exists. A unique mix of grasses, sedges, herbs, and low shrubs adapted to the cold, dry conditions. It supported enormous populations of herbivores, mammoths, bison, horses, reindeer, all grazing together. It must have been an incredible sight. Mammoths were iconic, but not alone. Woolly rhinoceroses were equally impressive, similar in size to modern rhinos, but built for the cold, with thick woolly coats and two horns, the front one sometimes over a meter long. They use these horns to clear snow and reach vegetation. Like mammoths, we found woolly rhinos preserved in permafrost with fur and soft tissue intact, showing clear adaptations to the extreme cold, including small ears and thick layers of fat. Giant ground sloths dominated the Americas. Modern sloths are cute, slow-moving animals in rainforest trees, but Ice Age ground sloths were different. The largest species, Megatherium americanum, weighed an estimated 3,800 kilograms, heavier than most elephants. They could stand on their hind legs, reaching heights of 4 meters or more. These were elephant-sized sloths, too big to climb trees, living on the ground and feeding on vegetation. And here's where it gets really interesting. We found their burrows, actual tunnels dug into hillsides, some 40 meters long and nearly 2 meters wide. Imagine stumbling upon a tunnel in the earth, and then imagine a multi-ton sloth emerging from it. It sounds like something from a fantasy novel, doesn't it? But these burrows are real. The walls and ceilings bear claw marks that match ground sloth claws perfectly. Scientists believe these sloths dug them to escape extreme temperatures or hide from predators. Another bizarre group was the glyptodons. Relatives of modern armadillos, but scaled up to ridiculous proportions. They weighed up to 2 tons and walked on elephant-sized legs. Their bodies were protected by shells made of hundreds of bony plates fused together like a turtle, but much larger and heavier. These shells could be over 1.5 meters long and tough enough to stop almost any predator. Some species even had tails covered in bony rings with spikes on the end, a medieval mace attached to their body. Biomechanical studies suggest they could rear up on their hind legs, armored tanks standing upright and swinging their spiked tails as weapons. The diversity of megafauna during the Ice Age is staggering. In North America alone, you had mammoths, mastodons, a different family of proboscideans with different tooth structures, American horses, American camels, giant beavers the size of bears, stag moose with enormous antlers, and multiple species of giant ground sloths. In South America, there were even more ground sloth species, glyptodons, giant armadillos, toxodons, which were kind of like hippo-sized rodent relatives, and Macrauchenia, which looked like a weird cross between a camel and a small elephant with a trunk. In Eurasia, you had mammoths, woolly rhinos, cave bears, steppe bison, giant deer called megaloceros, with antlers spanning over 3.5 meters and more. And then there were the predators. Wherever you have large herbivores, you have large carnivores hunting them. Saber-toothed cats are probably the most famous Ice Age predator. Smilodon in the Americas had those incredible canine teeth, up to 18 centimeters long and flattened like blades. These weren't for crushing bone or gripping. They were precision killing tools. Saber-tooths would use their powerful forelimbs to wrestle prey to the ground, then deliver a killing bite to the throat or belly, severing major blood vessels and causing rapid death from blood loss. The La Brea tar pits in California have preserved thousands of Ice Age animal bones, and saber-tooths are among the most common carnivores found there. This tells us they were successful predators, probably living in social groups like modern lions. And their prey wasn't small. They were taking down bison, young mammoths, horses, giant ground sloths, big, dangerous animals. Cave lions in Europe and Asia were larger than modern African lions and probably hunted similar prey. Cave bears, despite the scary name, were mostly herbivorous, but they were huge, up to half a ton, and their size alone made them formidable. And then there were giant short-faced bears in North America, which might have been the largest mammalian land predators ever to exist. These bears stood over 3 meters tall on their hind legs and may have weighed up to 800 kilograms. There's debate about whether they were active predators or scavengers, but either way, you definitely didn't want to run into one. Dire wolves were another major predator, especially in the Americas. Real dire wolves, not the fantasy version. They were larger and more heavily built than modern gray wolves, with more powerful jaws designed for crushing bone. They hunted in packs and could take down prey much larger than themselves through coordinated attacks. The La Brea tar pits have yielded thousands of dire wolf fossils, more than any other carnivore, which suggests they were incredibly common. Even birds got in on the megafauna action. Teratorns were some of the largest flying birds ever, with wingspans over 3.5 meters. They probably soared on thermals like modern condors, searching for carrion, and there were even larger flightless birds in some regions. The Ice Age world had no shortage of impressive and terrifying predators. But here's what's really fascinating. All of these animals, from the smallest ground squirrels to the largest mammoths, were part of functioning ecosystems. They weren't just wandering around randomly. They had complex relationships with each other and with their environment. Herbivores competed for food and space. Predators hunted herbivores. Scavengers cleaned up the remains. Plants evolved to withstand grazing prey. It was all interconnected. The megafauna themselves were ecosystem engineers. Mammoths, for example, didn't just eat grass. They knocked down trees, creating and maintaining open grasslands. They distributed nutrients across the landscape through their dung. They created trails and wallows. Their actions shaped the entire ecosystem. When you have animals that weigh several tons moving through an environment, they have a huge impact. Scientists have reconstructed these ancient ecosystems using multiple lines of evidence. Fossil assemblages tell us which animals live together in the same places. Isotope analysis of bones and teeth tells us what they ate and what the climate was like. Ancient DNA can be extracted from permafrost sediments, even from sediments with no visible fossils. And this tells us which species were present. Cave paintings created by humans show what animals looked like and how they behaved. By combining all this evidence, we can paint a pretty detailed picture of Ice Age life. One thing that's become clear is that these ecosystems weren't static. They changed and shifted as the climate fluctuated. Remember, even within a glacial period, there were shorter-term climate variations. Events called Dansgaard-Oeschger oscillations caused rapid warming spikes lasting decades to centuries, then rapid cooling again. The world of the Ice Age was never static. It was a constant dance of adaptation, a response to climate changes unfolding on multiple scales. Our own ancestors were players in this drama, living alongside mammoths and other megafauna, hunting them, competing with predators, and shaping their cultures to survive in glacial conditions. In Europe, Neanderthals had already weathered these cycles for hundreds of thousands of years. They were beings of the cold, with stocky builds and large nasal cavities to warm the frigid air. They were also beings of ingenuity, crafting sophisticated tools and weapons, mastering fire, and even expressing symbolic thought through art and burial rituals. Then, around 45,000 years ago, modern humans, Homo sapiens, arrived on the scene, bringing new technologies, more intricate social structures, and wider trade networks. For thousands of years, we overlapped with the Neanderthals, sharing the same landscapes and the same megafauna. And as we now know from genetic evidence, we even interbred. Most people of European or Asian descent carry a small piece of that ancient connection within them, about 1 to 2% Neanderthal DNA. In other corners of the world, modern humans were also adapting to the Ice Age, coexisting with megafauna in Asia, Australia, which humans reached at least 65,000 years ago, and eventually the Americas. The interaction between humans and these giant creatures is a hotly debated topic in Ice Age research, one we'll explore later. But for now, just try to imagine the sheer strangeness and diversity of life during that peak glaciation. Picture yourself standing at the edge of the last glacial maximum, gazing out over a landscape of ice sheets and cold grasslands with mammoths, rhinos, and giant sloths lumbering through it. You'd be witnessing a scene that will likely never exist again. These ecosystems are gone now. The megafauna are extinct. The mammoth steppe has vanished, replaced by forests and tundra. It's a lost world. But that world was sculpted by the 100,000-year cycle. The cold phases of that cycle created the very conditions to which life adapted, filling every available niche. For hundreds of millennia, this pattern repeated itself. Cold phase, megafauna thrive. Warm phase, forests expand. Cold phase again, the megafauna return. It was a rhythm that life on Earth had grown accustomed to. Then, about 19,000 years ago, something began to shift. The orbital cycles were moving into a configuration that favored warming. Summers in the Northern Hemisphere grew stronger, the ice sheets began to melt, and what followed would change everything. The transition from the last glacial period to our current interglacial was one of the most dramatic climate shifts in recent Earth history. And caught in the middle of that transition were all those megafauna, creatures that had evolved to thrive in a frozen world. Sadly, most of them wouldn't make it through. We've discussed what these Ice Age giants looked like, but let's delve into the details of how they actually lived. The more we uncover about these animals, the more astonishing they become. Some of the discoveries are genuinely surprising. Take, for instance, something that seems almost impossible: giant ground sloths digging massive burrows. When scientists first stumbled upon these tunnels in South America, particularly in Argentina near Mar del Plata, they were baffled. The burrows were enormous, some plunging 5 to 6 meters below the surface, stretching up to 1.8 meters wide and 40 meters long. That's the equivalent of a 2-story house worth of tunnel hidden beneath the ground. Multiple mammal species were considered as the possible architects of these burrows. But the evidence kept pointing back to ground sloths, specifically species like Glossotherium and Celidotherium. The first clue was their arm bones. Ground sloth forelimbs were designed in a shovel-like structure, with unusually long second and third fingers, perfectly suited for digging, and the bones themselves were incredibly strong, designed to withstand the bending forces that come with digging through hard soil, similar to the stresses that galloping mammals put on their leg bones. The second clue was their center of gravity. Paleontologists estimated that ground sloths had their center of gravity positioned above their hind feet, which meant they could rear up into a bipedal posture. This is crucial for digging because your arms need to be free to excavate, not supporting your body weight. You simply can't dig effectively on all fours. And the final, undeniable piece of evidence: claw marks on the walls and ceilings of the burrows, perfectly preserved in the fossilized tunnels. Scientists matched these marks to ground sloth hand skeletons, and the fit was exact. These sloths weren't just big. They were engineering huge underground structures despite weighing 800 to 200 kilograms. It's incredible behavior. Why were they doing it? The leading theories revolve around temperature regulation or predator avoidance. Underground, temperatures are far more stable than on the surface. If you're trying to escape extreme heat or cold, a burrow makes perfect sense. Or perhaps they were seeking refuge from predators like saber-toothed cats or giant short-faced bears. When you're big but not fast, going underground where predators can't easily follow is a clever strategy. Either way, it demonstrates that these animals were far more behaviorally complex than we might expect from something called a giant sloth. Here's another fascinating discovery about ground sloths. In Ecuador, at a site called Tanque Loma, paleontologists unearthed the remains of at least 22 Eremotherium sloths of various ages, all in the same location. It's likely they perished during a drought, becoming trapped in a shrinking watering hole. But the remarkable part is what this tells us about their behavior. They were congregating at watering holes, which suggests they were social animals living in groups. And they were probably wallowing in the water to escape the heat and insects, much like hippos and rhinos do today. The last mammoths lived on Wrangler Island in the Arctic Ocean. It's strange to think that as the pyramids of Giza were being built, a population of these giants, maybe 1,000 strong, still roamed a remote island. I can almost picture them, relics of a colder world as the Bronze Age dawned. Then, about 4,000 years ago, they vanished, victims of inbreeding, dwindling resources, and perhaps the arrival of humans or a change in the climate. It was the end of a line that stretched back millions of years. Even during the Ice Age, not everywhere was frozen. Tropical and subtropical regions still experienced warm seasons. It was cooler and drier than today, but those equatorial regions weren't entirely under ice sheets. Animals living there still had to deal with heat stress. Ground sloths in South America, for example, use similar strategies to large African mammals today. The Ice Age wasn't a monolithic block of ice across the entire planet. And we keep learning new things about mammoths, especially those preserved in the Siberian permafrost. Some have even had their last meals preserved in their stomachs. Scientists have examined this material and found grasses, sedges, herbs, flowers, and mosses, painting a vivid picture of the mammoth steppe ecosystem. We've even extracted DNA from these frozen specimens, sequencing entire mammoth genomes. The genetic analysis has revealed some remarkable adaptations. Mammoths, it turns out, had variants of hemoglobin, the protein that carries oxygen in blood, that functioned better at cold temperatures. Normal hemoglobin doesn't release oxygen as efficiently when it's cold, a big problem for an animal in freezing conditions. Mammoth hemoglobin had mutations that compensated, allowing their blood to deliver oxygen even when their body tissues were cold. That's hardcore molecular adaptation. We've also found that mammoths had genes for small ears, sparse sweat glands, and improved fat storage, all coded in their DNA. Evolution didn't just change their external appearance, it rewired their physiology at the genetic level. Woolly rhinoceroses, like mammoths, had thick, woolly coats and were built for the cold. But their behavior was different, based on tooth wear and isotopes in their bones. Scientists believe woolly rhinos were more selective feeders than mammoths. Mammoths were bulk grazers, eating whatever vegetation was available, while woolly rhinos seemed pickier, using their horns to dig through snow for specific plants. The giant deer, Megaloceros, had antlers that were absolutely insane. The largest specimens had antlers spanning over 312 meters from tip to tip, wider than a car. These antlers could weigh up to 40 kilograms. Carrying that much weight takes serious neck and shoulder muscles. Scientists believe these massive antlers were primarily for display and competition between males, like modern deer. During mating season, males would show off their antlers to females and use them in battles with rivals. The bigger your antlers, the more impressive you looked, but those antlers came at a cost. Growing them required huge amounts of calcium and energy, and carrying them around was energetically expensive. Only the healthiest, best-fed males could support truly enormous antlers. Cave bears, despite their name and size, were mostly herbivorous. Isotope analysis of their bones shows they primarily ate plants. They were built like grizzly bears but acted more like giant pandas. They hibernated in caves during winter, where we find most of their fossils. Some caves in Europe have thousands of cave bear bones, representing hundreds or thousands of individuals that hibernated there over millennia. Cave bears went extinct earlier than many other megafauna, around 27,000 to 24,000 years ago, well before the end of the last glacial period. The reasons aren't entirely clear, but it might have been competition with humans for cave space, climate changes affecting their food supply, or a combination of factors. And the glyptodons, I'm still amazed by them. Recent studies of their skeletal structure and muscle attachment points suggest they were capable of some surprising behaviors. They might have been able to rear up, but they also show adaptations for powerful digging, similar to modern armadillos but scaled up massively. These armored giants might have dug burrows like their ground sloth contemporaries. Imagine tunnels big enough for a Volkswagen Beetle to drive through, created by armored animals with spiky tails. The Ice Age was truly wild. The predators of the Ice Age were just as specialized as the herbivores. Saber-toothed cats didn't just have those impressive fangs for show. Biomechanical studies of their skulls show they had relatively weak bite forces compared to modern big cats, but their neck muscles were incredibly powerful. Their hunting strategy was probably to use their strong forelimbs to wrestle prey down, then use their neck muscles to drive those saber teeth deep into the prey's throat or belly with precision. It wasn't about crushing force, but about precision. Imagine standing in the La Brea tar pits, surrounded by the ghosts of dire wolves. Thousands of them died here, trapped in the sticky asphalt over tens of thousands of years. They came to scavenge and became the scavenged. What their fossils reveal about their lives is truly fascinating. Many dire wolf specimens show broken teeth, healed fractures, and signs of arthritis, especially in the older ones. It suggests a social structure, a pack that cared for its injured. A wolf with a broken leg can't hunt alone, but a pack that shares food, that wolf survives. Giant short-faced bears, on the other hand, remain a puzzle. Were they predators or scavengers? Perhaps they were opportunistic, hunting when they could, scavenging when they had to. Their sheer size, potentially the largest mammalian land predator ever, suggests they could intimidate smaller predators, steal their kills. I picture a pack of dire wolves bringing down a bison, only for a giant short-faced bear to appear and chase them off. One of the coolest things about the Ice Age is the evidence we have from an unusual source: ancient DNA in sediments. Even without bones, DNA from animals can be preserved in frozen soil. Scientists extract and identify this environmental DNA, revealing which species lived where and when. It fills in the gaps in the fossil record, showing us that Ice Age ecosystems were even more diverse than we realized. We now know horses were present in areas where we have no horse fossils, all because we found horse DNA in the soil. We've identified plants that grew in certain regions by finding their pollen and DNA. We can even tell what the climate was like by looking at which species of plants and insects were present. It's like reading an ancient ecological record written in genetic code. And then there are the humans. They were observing and interacting with all of this megafauna, and they left records of what they saw. The cave art from sites like Lascaux in France and Chauvet Cave, the remarkably accurate depictions of Ice Age animals, mammoths, woolly rhinos, bison, horses, cave lions. These paintings aren't crude stick figures. They're sophisticated artworks showing animals in motion, using the natural contours of the cave walls to create three-dimensional effects. The artists clearly spent a lot of time observing these animals to capture them so accurately. Some cave paintings even show details like fur patterns, seasonal coat changes, and behavioral poses. There's a famous painting of a woolly rhino that clearly shows its thick fur and the way it held its head. There are paintings of mammoths that show their characteristic domed heads and long tusks. These artworks are our direct visual record of what Ice Age megafauna looked like, created by people who saw them alive. Humans also left behind butchered animal bones, showing clear-cut marks from stone tools, mammoth bones with spear points embedded in them, campsites with hearths surrounded by the remains of horses, bison, and reindeer. The archaeological record proves that humans hunted megafauna and relied on them for food, materials for tools and clothing, and fat for fuel. Mammoth ivory was carved into art objects and tools. Hides were used for clothing and shelter. Bones were used to build dwelling structures in areas with scarce wood. Every part of these animals was utilized. But humans weren't just passive observers or simple hunters. There's evidence that humans might have used fire to manage landscapes, creating and maintaining the open grasslands that megafauna depended on. By burning vegetation regularly, humans could prevent forests from encroaching on grasslands, keeping habitats open for the large herbivores they hunted. This kind of ecosystem engineering might have actually helped support megafauna populations in some regions. The relationship between humans and megafauna was complex, not just predator and prey. The 100,000-year cycle had created this entire world. The cold phase of the cycle produced these unique ecosystems and drove the evolution of specialized megafauna adapted to frozen conditions. For hundreds of thousands of years, the pattern repeated. Ice sheets advanced. Megafauna thrived. Ice sheets retreated. Forests expanded. Ice sheets advanced again. Life adapted to this rhythm. But then, about 19,000 years ago, the cycle began shifting toward warming again. And this time, something was different. This time, humans had spread across most of the world, developed sophisticated hunting technologies, and existed in larger numbers than ever before. This time, when the climate started changing and the ice began to melt, the megafauna wouldn't just adapt and wait for the cycle to swing back to cold like they had for hundreds of thousands of years. This time, most of them were going to disappear forever, and we're still debating exactly why. So, around 19,000 years ago, the 100,000-year cycle reached a turning point. The orbital configuration shifted into a pattern that favored warming. Northern Hemisphere summers started getting stronger, receiving more solar radiation. And when that happens, winter snow starts melting more completely each summer. Ice sheets stop growing and begin their long retreat. The transition from glacial to interglacial conditions was underway. Deglaciation isn't a smooth process. It's messy, full of fits and starts, sudden collapses, and even temporary reversals. There are periods of such rapid change that they would have been noticeable within a single human lifetime. And this messiness is exactly what makes understanding the extinction of the megafauna so complicated. The first major pulse of melting occurred around 19,000 years ago and continued for several millennia. As the ice sheets melted, sea levels rose. During one period, around 14,600 years ago, called Meltwater Pulse 1A, sea levels rose roughly 20 meters in less than 500 years. 20 meters might not sound like much, but that's enough to flood vast coastal areas, submerge land bridges, and completely transform coastlines. All that water had to come from somewhere, and it came from the collapsing edges of the great ice sheets. The Laurentide ice sheet, that massive dome of ice covering Canada, began breaking apart. The Fennoscandian ice sheet in Europe did the same. As they melted, they left behind a landscape that had been compressed under kilometers of ice for thousands of years. The land was scraped clean, covered in glacial till, and dotted with lakes formed in depressions carved by ice. I imagine it must have been a raw, bare landscape at first, slowly being colonized by plants as the climate warmed. But the warming wasn't steady. There were dramatic interruptions, the most famous being the Younger Dryas event. By around 14,700 years ago, the world had been warming for thousands of years. Ice sheets were in retreat. Things seemed to be heading toward interglacial conditions. Then suddenly, temperatures crashed. In Greenland, temperatures dropped by about 15 degrees Celsius in just a few decades, possibly faster. Some evidence suggests it could have happened in as little as 10 to 20 years. The North Atlantic region was plunged back into near glacial conditions that lasted over 1,000 years. The leading theory involves a catastrophic flood. As the Laurentide ice sheet melted, water pooled up behind it, forming enormous glacial lakes. The largest was Glacial Lake Agassiz, which was bigger than all of the modern Great Lakes combined. This lake was dammed in by the ice sheet itself, and when that ice dam failed, geological evidence suggests it did multiple times. Absolutely stupendous amounts of fresh water flooded into the ocean in a geologically instant time frame. We're talking about enough water to raise global sea levels by several meters, all released in months to years. This massive freshwater dump disrupted ocean circulation in the North Atlantic. There's this ocean circulation pattern called the Atlantic Meridional Overturning Circulation, or AMOC. It's basically a conveyor belt where warm surface water flows north, cools down near Greenland, becomes dense and sinks, then flows south at depth. This circulation transports enormous amounts of heat from the tropics to the Northern Hemisphere, but fresh water is less dense than salt water. When you dump a huge amount of fresh water into the North Atlantic, it floats on top and prevents the normal sinking of cold, dense water. This can slow down or shut down the AMOC, and when the AMOC stops, the Northern Hemisphere stops receiving that massive heat transport from the tropics. Temperatures crash, and you're back to near glacial conditions. The Younger Dryas had effects far beyond the North Atlantic. Climate patterns shifted across the globe. Some regions got drier, others wetter, temperatures changed, and this had huge impacts on ecosystems and the animals living in them. For megafauna that were already stressed by changing habitats as the climate warmed and forests expanded, the Younger Dryas cold snap might have provided a temporary reprieve, but it also added instability to an already unstable situation. And it had major impacts on human societies, too. In the Middle East, this is right around the time agriculture first developed. Some scientists think the climate stress of the Younger Dryas might have pushed hunter-gatherer groups to start deliberately cultivating plants as a way to end food security when wild resources became unreliable. If that's true, then this climate event, triggered by the 100,000-year cycle transitioning from glacial to interglacial, literally changed the course of human history, setting us on the path to farming, settled civilizations, and everything that followed. But eventually, around 11,700 years ago, the Younger Dryas ended, and it ended just as abruptly as it started. Temperatures spiked upward again. In some regions, temperatures rose by 10 degrees Celsius or more in just a decade or two. That's mind-bogglingly fast for natural climate change. The AMOC kicked back into gear. Heat flooded northward again. Ice sheets resumed their collapse, and this time there was no going back. The transition to full interglacial conditions was complete. We call this the beginning of the Holocene, our current geological epoch, and it marks the end of the last glacial period. For the megafauna, this was catastrophic. They had evolved over hundreds of thousands of years to thrive in cold, open grassland environments. But as the Holocene began, those environments were disappearing. The mammoth steppe, that unique ecosystem of cold grasslands that had supported enormous populations of large herbivores, was transforming. Forests were expanding. Grasslands were shrinking. The climate was getting wetter and warmer. For animals adapted to cold and dry conditions, this was a crisis, and the extinctions came fast. In North America, most megafauna disappeared between about 13,000 and 11,000 years ago. Mammoths, mastodons, horses, camels, giant ground sloths, saber-toothed cats, dire wolves, giant short-faced bears, all gone within a few thousand years. That's 70 to 80% of large mammal species just vanished. It was called the Quaternary Extinction Event, and it was truly devastating. Giant ground sloths vanished from South America. Gone, too, were the glyptodonts, the native horses and camels, the toxodons, the macrochenia, and the giant armadillos. In fact, an extinction wave swept through the Americas like wildfire. Even earlier, Australia had lost most of its megafauna between 50 and 40,000 years ago. Giant wombats, enormous kangaroos, massive flightless birds, and even a marsupial lion all disappeared. The timing in Australia seems to coincide more with human arrival than with the last deglaciation. This adds another piece to the puzzle of what caused these extinctions. So, what killed them? That's the question that's been debated for decades. Honestly, it's still not completely settled. There are two main schools of thought: the climate change hypothesis and the human hunting hypothesis. The truth, I suspect, is probably a combination of both, with the relative importance varying by region and species. The climate change hypothesis argues that the rapid warming and ecosystem transformation was simply more than these animals could handle. Megafauna had evolved for cold, open habitats. When those habitats disappeared in just a few thousand years, they couldn't adapt quickly enough. As forests expanded and grassland shrank, megafauna populations became fragmented into smaller and smaller pockets of suitable habitat. Small, isolated populations are vulnerable to inbreeding, disease, and random environmental fluctuations. This creates an extinction vortex where declining populations face multiple threats that compound each other, and recovery becomes impossible. There's good evidence for climate being a major factor. The extinctions happened during a period of incredibly rapid climate change. Species adapted to cold climates, like woolly mammoths and woolly rhinos, went extinct, while species adapted to forests or warmer climates generally survived. This pattern suggests climate played a big role. Also, megafauna had survived previous deglaciations. The 100,000-year cycle means there were multiple transitions from glacial to interglacial conditions over the past few million years. If megafauna survived those, why not this one? That's where the human hunting hypothesis comes in. Modern humans had spread across most of the world by the end of the last ice age. And humans are incredibly effective hunters, especially with the technological innovations that developed during this period. Atlatls, spear throwers that dramatically extend your range and power. Sophisticated hunting strategies involving coordinated groups, and later, bows and arrows. Human populations were growing and spreading into new territories. Critically, many megafauna had little or no evolutionary experience with human hunters when humans first arrived in the Americas or Australia. The local megafauna hadn't evolved fear responses to these two-legged predators. They were naive prey. Modern examples show this pattern. When humans first reached oceanic islands with no previous human presence, the native birds and mammals often showed no fear and were easily hunted to extinction within decades or centuries. The same might have happened with Ice Age megafauna. They simply didn't recognize humans as threats until it was too late. And here's the thing about hunting megafauna. You don't need to hunt intensively to drive them extinct. These animals have slow reproductive rates. A female mammoth might have a calf every 5 years. Mammoths don't reach sexual maturity until they're teens. If you kill even a few individuals per year from a population, especially females of reproductive age, you can drive the population into decline. Mathematical models show that even very low-intensity hunting, killing just a few % of the population per year, can drive large-bodied animals extinct over centuries to millennia. And we know humans hunted megafauna. We found butchered mammoth bones at human sites, spear points embedded in mammoth ribs, kill sites where multiple animals were driven off cliffs or into traps and then butchered, and cave paintings showing hunting scenes. The evidence is undeniable that humans hunted these animals. The question is whether hunting alone could cause extinctions or whether it was just the final straw for populations already struggling with climate change. The timing is really suspicious in many regions. In North America, the extinctions coincide almost exactly with the expansion of Clovis culture, a group of humans with particularly effective hunting technology. Clovis points, these distinctive spear points, are found at sites with butchered mammoth remains. Within a few thousand years of Clovis people spreading across North America, the megafauna were gone. That's awfully coincidental timing. A study of the Anzac child, the only known Clovis individual, provides some interesting evidence. This was an 18-month-old child buried about 12,700 years ago in Montana. Scientists analyzed isotopes from the bones to reconstruct the diet of the child's mother. They found that mammoth contributed around 40% of the maternal protein diet, similar to the diet of specialized mammoth predators like scimitar cats. This suggests Clovis people were heavily targeting mammoths, possibly as specialized mammoth hunters. But we need to be careful not to overinterpret. The Anzac child is one individual. We can't say all Clovis people had the same diet or hunting focus. The disappearance of the Ice Age giants, it's not a simple story. Even now, there's still debate about just how many humans there were at the time and whether such relatively small populations could have really hunted mammoths to extinction across an entire continent. Some scientists remain skeptical. What I find so compelling is that the extinction pattern itself isn't uniform. Some species vanished early, while others held on longer. Mammoths, for example, survived on Wrangler Island until around 4,000 years ago, thousands of years after they had disappeared from the mainland. And cave bears? They went extinct even before many other species. It's a puzzle. Dire wolves disappeared, but gray wolves managed to survive. Bison were heavily hunted, and yet they also persisted. The reasons why some species made it while others didn't are still being investigated. But one thing seems increasingly clear. The combination of climate change and human proved deadly. Climate change stressed these megafauna populations, fragmenting their habitats and reducing their food sources. Then, human hunting prevented these already struggling populations from ever recovering. It was, in effect, a perfect storm that most megafauna simply couldn't weather. And there may have been indirect effects that we are only now beginning to understand. Humans extensively used fire to manage landscapes, which altered vegetation patterns. The loss of the megafauna themselves had profound ecosystem effects. Mammoths and other large herbivores acted as ecosystem engineers, maintaining open grasslands. When they disappeared, these grasslands transformed into forests, making the habitat even less suitable for any remaining megafauna. It's a cascade of interconnected effects. What we're left with is this. The 100,000-year cycle sustained megafauna for hundreds of thousands of years. During cold phases, they thrived. During warm phases, they retreated to refugia. And then, during the next cold phase, they expanded again. Life had adapted to this rhythm. But this time, when the cycle shifted to warming, there was a new factor. Humans, with sophisticated hunting technology and growing populations. The combination of rapid climate change and human press was more than most megafauna could handle. And within a few thousand years, the Ice Age world of giants was gone forever. Now, let's turn our attention to the humans who lived through these 100,000-year cycles, because their story is just as fascinating as that of the megafauna. And when I say humans, I'm talking about multiple species. We weren't the only ones around during the Ice Age. Neanderthals were already well established when our ancestors showed up, and they deserve far more credit than they usually receive. Neanderthals were, in a very real sense, the original Ice Age survivors. They evolved in Europe and parts of Asia hundreds of thousands of years ago and had been living through these glacial cycles long before modern humans ever left Africa. They weren't some brutish, primitive dead end. They were sophisticated, intelligent humans who had adapted incredibly well to glacial conditions. Their adaptations were, quite frankly, brilliant. Start with their body structure. Neanderthals were short and stocky, with barrel chests and thick, heavy bones. The average male was only about 160 centimeters tall, but they were built like tanks, seriously muscular, with bones showing massive muscle attachment sites. This wasn't random, it was an adaptation to the cold. Shorter, stockier bodies have less surface area relative to their volume, which means less heat loss. This is Bergmann's rule in action, the same principle that made Ice Age megafauna so large. In cold climates, compact bodies retain heat better, and their faces were distinctive, with large noses and wide nasal passages. This wasn't for aesthetics. Those big nasal cavities acted like built-in air conditioners, warming and humidifying the frigid, dry air before it reached the lungs. Breathing super cold air repeatedly can damage lung tissue, so this was crucial. It's the same adaptation we see in woolly mammoths with their enlarged sinuses. Different species, same solution to the same problem. Convergent evolution at work. But physical adaptations only tell part of the story. Neanderthals had sophisticated culture and technology. They made complex stone tools using the Levallois technique, where you carefully prepare a core and then strike off flakes of predetermined shapes. This requires planning and mental visualization. You have to see the finished tool in your mind before you start working the stone. They also made wooden spears, carefully shaped and balanced, with tips hardened by fire. Some of these spears have been found preserved in German peat bogs, and they're beautifully crafted. And Neanderthals hunted big, dangerous game. We found Neanderthal sites with bones of bison, reindeer, wild horses, even woolly rhinoceros and mammoth. These weren't scavenged carcasses. The bones show clear butchery marks made with stone tools while the meat was fresh. Neanderthals were actively hunting animals that could easily kill them if the hunt went wrong. That requires coordination, communication, planning, and courage. They used fire extensively and effectively, not just for warmth and cooking, but for making complex adhesives. Archaeologists have found Neanderthal tools with birch bark tar used to attach stone points to wooden handles. Making birch bark tar requires heating birch bark in the absence of oxygen at specific temperatures. This is a multi-step process that requires technical knowledge and careful control. You can't just stumble into figuring this out. They understood the process and could replicate it reliably. Even more impressive, Neanderthals had symbolic culture. They made ornamental objects, pierced shells, and eagle talons that were apparently worn as jewelry. They used pigments, possibly for body painting or decorating objects or cave walls, and they buried their dead, sometimes with what appear to be grave goods or in deliberate postures. There's a famous burial at Shanidar Cave in Iraq that includes evidence that might suggest flowers were placed in the grave, though that's still debated. I often find myself wondering about the last days of the Neanderthals. What was it like to be among the last of their kind? The intentional burial of their dead tells us they thought about death and had rituals. That's a deeply human behavior. They even created art. In Spanish caves, I've seen the abstract geometric patterns and hand stencils they left behind, dating back to when only Neanderthals were present. These are some of the earliest examples of cave art, pushing back the timeline of symbolic thought. It wasn't just one group doing something strange either. Similar markings have been found at multiple sites, suggesting it was part of a broader Neanderthal culture. So, if Neanderthals were so capable and well-adapted, why did they disappear? It's a question paleoanthropologists still debate. The last Neanderthals died out around 40,000 years ago, just as modern humans were spreading into Europe from Africa and the Middle East. The timing is suspicious. Did we outcompete them? Absorb them through interbreeding? Kill them off directly? Or was it something else entirely? The genetic evidence is clear that Neanderthals and modern humans interbred. If you're of European or Asian descent, you probably carry 1 to 2% Neanderthal DNA. It might not sound like much, but it proves our ancestors and Neanderthals were having children together, children who survived and had their own children. Some Neanderthal genes are still with us today, including variants that affect immune function, skin and hair traits, and even susceptibility to certain diseases. So, at some level, Neanderthals didn't completely go extinct. They were absorbed into the modern human gene pool. But as a distinct population with their own culture and identity, Neanderthals didn't survive. Why? One major factor was probably demographics. Modern human populations seem to have been larger and more widespread. When two populations are competing for the same resources, the one with more individuals usually wins through sheer numbers. Even if individual Neanderthals were just as capable as individual modern humans, If they were outnumbered 10 to 1, they'd eventually be swamped by the larger population. Modern humans also seem to have had some technological advantages. While Neanderthals made excellent tools, modern humans developed more diverse and specialized toolkits. They made fine bone needles for sewing-fitted clothing, which provided better insulation than just wrapping hides around yourself. They made fishing equipment like hooks and harpoons, expanding their food sources. They created more prolific art and ornaments, possibly indicating more complex social structures or better communication systems. Modern humans also had wider trade networks. We find materials at modern human sites that came from hundreds of kilometers away, showing they were exchanging goods over large distances, while Neanderthal trade networks were more localized. Trade isn't just about stuff. It's about information exchange and social connections. Wider networks mean more people sharing ideas and innovations, which accelerates cultural evolution and adaptation. Some researchers think modern humans might have had slightly better language abilities, allowing more complex planning and coordination. Or maybe they had different social structures that were more effective at resource acquisition or raising children. These are subtle differences that wouldn't show up obviously in archaeological remains, but over generations, they could compound into significant advantages. Climate might have played a role, too. The late Ice Age was incredibly unstable climatically, with rapid swings between cold and warm. Maybe Neanderthals, who were specialized for cold, stable conditions, struggled more with rapid climate fluctuations. Modern humans coming from Africa, which had its own climate variability, might have been more adaptable to changing conditions. But this is speculative. We don't really know. What's clear is that by 40,000 years ago, Neanderthals were gone, and modern humans were the only human species left in Europe. And modern humans were spreading everywhere, adapting to every environment Earth had to offer. By the end of the last glacial period, humans had reached every continent except Antarctica, and they'd done it while surviving the 100,000-year cycle at its most extreme phase. Modern humans developed an impressive array of technologies during the late Ice Age. Projectile weapons were a game-changer. Early humans used thrusting spears that required getting close to prey. Dangerous when you're hunting mammoth. Then they invented the atlatl, a spear thrower that acts as a lever arm to dramatically increase throwing range and power. Suddenly, you could attack from tens of meters away, much safer. Later, probably between 20 and 30,000 years ago in some regions, humans invented the bow and arrow. This was huge. Arrows are faster and more accurate than atlatl darts. You can carry more ammunition. You can hunt smaller, faster animals more effectively. The bow might be one of the most important technological innovations in human history. It fundamentally changed how humans could acquire food and defend themselves. Hunting strategies became more sophisticated, too. There's evidence of drive hunting, where groups would herd animals toward cliffs or into constructed traps, sites with hundreds of bison or horses that were driven off cliffs and butchered. This requires serious coordination among large groups of people. You need scouts, drivers, people positioned at the cliff to finish off injured animals, butchers, all working together with precise timing. It's complex social behavior that requires communication and planning. Fishing also became important. Humans developed harpoons. fish hooks made from bone, nets, and we opened up aquatic resources as a resource. Ice Age humans weren't just struggling to survive. They had rich inner lives, spiritual beliefs, and complex cultural traditions. They were, in essence, fully modern people mentally and behaviorally, even though they lived in conditions we would find incredibly harsh. Thinking about the art they created still amazes me. One thing that helped early humans thrive was their diet. Fish became a major food source, especially in coastal and river areas. Fishing was relatively low risk compared to hunting mammoths. Coastal sites reveal intensive use of fish and shellfish, with enormous shell middens representing thousands upon thousands of meals. Clothing technology also improved dramatically. Those bone needles that appear around 40,000 years ago were for sewing fitted clothing with sleeves and clothes. If you've ever tried just wrapping animal hides around yourself to stay warm, you know it's not very effective. Fitted clothing is far better at trapping body heat. This technology probably allowed humans to survive in even colder regions and remain active during winter instead of just hunkering down. Shelter evolved, too. In regions with scarce wood, people built structures using mammoth bones and tusks as a framework, covered with hides. These mammoth bone houses have been found in Ukraine and Russia. Some used bones from dozens of individual mammoths, representing thousands of kilograms of material. These were substantial dwellings, not temporary camps. People were investing serious effort into creating comfortable long-term living spaces. And then there's the art. Ice Age humans created stunning artwork. Cave paintings like those at Lascaux and Chauvet in France are justly famous. These aren't crude drawings. They're sophisticated, dynamic images of animals rendered with incredible skill and accuracy. The artists used the natural contours of cave walls to create three-dimensional effects. They mixed pigments to achieve different colors and understood techniques like shading and perspective. Some paintings even show animals in motion, running or fighting, capturing movement in a static image. But it wasn't just cave paintings. People carved figurines from ivory, bone, and stone. The Venus figurines, stylized female forms found across Europe, date to this period. Some have elaborate details like hairstyles or clothing carved into them. People made musical instruments too. Flutes carved from bird bones or mammoth ivory. They created elaborate burials with grave goods, including thousands of ivory beads sewn onto clothing. One burial of children at Sungir in Russia included so many beads that researchers estimated it would have taken thousands of hours to make them. These people valued symbolic expression enough to invest enormous time and effort into it. Why did humans create art? Probably for lots of reasons. Some cave art might have been connected to hunting magic or spiritual rituals. Some figurines might have been religious or fertility symbols. Some art was probably just for aesthetic plea or social bonding. Human populations during the Ice Age weren't huge by modern standards. Estimates suggest maybe just a few million people worldwide. But those people had spread across most habitable regions. They'd reached Australia by at least 65,000 years ago, crossing significant water gaps even during low sea levels. They'd spread throughout Asia and Europe, and critically, they'd made it to the Americas. The peopling of the Americas is fascinating. During peak glaciation, when sea levels were low, the Bering Land Bridge connected Asia and North America. But this wasn't just a narrow strip. Beringia was a vast region, probably thousands of kilometers wide, with its own ecosystems. Humans crossed it, probably following game animals, entering a continent with no previous human population and megafauna that had never encountered human hunters. The timing is still debated. The oldest widely accepted sites in the Americas date to about 15 to 16,000 years ago, but there are controversial sites that might be older, suggesting people could have arrived as early as 20 to 30,000 years ago. Either way, once humans were in the Americas, they spread incredibly fast. Within just a few thousand years, there's evidence of human presence from Alaska to the southern tip of South America. That's an incredible migration speed. And remember, the American megafauna went extinct shortly after humans arrived. Mammoths, mastodons, giant ground sloths, horses, camels, all gone within a few thousand years of human appearance. The timing suggests humans played a major role. The Clovis people, with their distinctive spear points and apparent focus on hunting mammoths, have been particularly implicated. But it's complicated. Climate was changing rapidly at the same time. It's probably both factors working together. By the time the Holocene began 11,700 years ago, humans were the dominant large animal on multiple continents. We'd outlasted Neanderthals and other human species. We'd survived the wild climate swings of deglaciation. We'd adapted to every environment from tropical rainforest to Arctic tundra. And we developed incredibly diverse cultures and technologies. Despite being one species genetically, humans showed cultural diversity that no other species has ever matched. This set the stage for what came next: the development of agriculture and the rise of civilization. But that's a different chapter in the story. The point is, the Ice Age and its 100,000-year cycle was the crucible that forged modern human behavior. The technological innovations, the social structures, the symbolic thinking, all developed or were refined during the harsh conditions of glacial cycles. We are in a very real sense products of the Ice Age. Our success as a species was built on adaptations to a frozen world, and now that world is gone, melted away as the cycle shifted to its warm phase. The question is, I often wonder if we're truly adapted to the world we inhabit now, or if we're still carrying baggage from an ice age that ended millennia ago. The shift from the 100,000-year cycle is profound. The ice melted, the megafauna vanished, and humans now live in a world unrecognizable to our ancestors. It's all part of the Holocene, our current interglacial period, and it marked a turning point for human societies. Around 11,700 years ago, the Younger Dryas cold snap finally released its grip. Temperatures rose swiftly, stabilizing into conditions remarkably similar to today's. The climate became warmer and wetter than it had been during the glacial period. Forests expanded, carpeting areas that were once cold grasslands and tundra. Sea levels continued their ascent as the last major ice sheets melted, reshaping coastlines into the geography we recognize. The transformation was dramatic and relatively fast. For humans, who had existed as hunter-gatherers for so long, this new era presented both opportunities and challenges. Warmer temperatures meant longer growing seasons, more diverse vegetation, and a more predictable climate. but the megafauna they had hunted were disappearing. Those massive herds of mammoth, bison, and horses, once reliable food sources, were gone or facing extinction. Humans had to adapt their subsistence strategies, and they had to do it quickly. In some regions, people turned to fishing and gathering shellfish. Coastal sites from this period are filled with enormous shell middens and fish bone deposits. The ocean was stable and productive, providing a reliable food source. In other regions, people focused on smaller game like deer, rabbits, and birds, supplemented with gathered nuts, seeds, roots, and berries. These resources required different hunting techniques than megafauna hunting. You can't drive deer off cliffs. You need different tools, different strategies. But in a few special regions, something revolutionary happened. People began deliberately planting and cultivating wild plants. This was the dawn of agriculture, and it would change everything about human society. The earliest clear evidence of agriculture appears in the Fertile Crescent of the Middle East, around 11 to 10,000 years ago. People began cultivating wheat and barley, domesticating sheep and goats. In China, rice and millet cultivation began around 9,000 years ago. In Mesoamerica, maize was domesticated around the same time, in multiple regions independently. Within just a few thousand years of each other, humans invented farming. Why did agriculture develop when it did? That's a question that has been debated for ages. One theory centers on population pres. During the Ice Age, human populations were kept relatively small by harsh conditions and limited food resources. But as the Holocene began and conditions improved, populations may have grown to the point where hunting and gathering could no longer support everyone. Agriculture produces more calories per unit of land than hunting and gathering, so it can sustain higher population densities. If your population outgrows your hunting territory, you either starve, migrate, or innovate. Some groups chose innovation. Another theory emphasizes climate stability. Agriculture requires planning for the future. You plant seeds and wait months for the harvest. This only makes sense if you can reasonably predict that conditions will remain suitable for plant growth. During the wildly fluctuating climate of the late Ice Age, with events like the Younger Dryas, that wasn't a safe bet. But during the Holocene, climate became more stable and predictable. You could plant in spring and be reasonably confident summer would come and your crops would mature. This stability made agriculture viable in a way it hadn't been before. There's also a theory that the Younger Dryas specifically triggered agriculture in the Middle East. The idea is that hunter-gatherers in the Fertile Crescent had developed semi-sedentary lifestyles during the warm period before the Younger Dryas, living in villages and intensively harvesting wild grains. Then the Younger Dryas hit, and those wild grains became less productive. To maintain their lifestyles and avoid starvation, people started actively cultivating the grains, selecting for varieties that produced more food. When the Younger Dryas ended, they were already farming and simply continued. Whatever triggered it, agriculture spread rapidly once it started, and it came with a massive package of changes to human society. You can't be nomadic and farm effectively. You need to stay in one place to tend crops and protect them from animals and thieves. So agriculture led to permanent settlements, villages that grew into towns and eventually cities. These settlements required new forms of social organization. Who controls the land? How do you store surplus food? How do you defend your settlement? How do you resolve disputes? Agriculture also changed human diets dramatically, and not always for the better. Hunter-gatherers typically had diverse diets with lots of protein and varied nutrients from many plant and animal sources. Early farmers ate mostly carbohydrates from a few grain crops, supplemented with whatever else they could grow or gather. Skeletons from early agricultural societies show signs of nutritional stress compared to hunter-gatherers. More cavities from all the starchy foods, shorter average stature, diseases associated with dietary deficiencies. Agriculture allowed population growth, but individual health often declined. Disease became a much bigger problem once humans started living in permanent settlements. When you're nomadic and moving frequently, your waste gets left behind, and diseases don't have time to build up. But in permanent villages, the shift from hunter-gatherer to agricultural societies wasn't just a change in how we found food, it was a complete transformation of our world. I find it fascinating to consider that many of the diseases that plague us today, like measles and smallpox, originated in the very animals we domesticated. Living in close quarters with high population densities and waste accumulation created the perfect storm for infectious diseases to thrive. It's a sobering thought, isn't it? But agriculture's overwhelming advantage was simple. It could support so many more people. A square kilometer of wheat could feed dozens, even hundreds, where the same land as wilderness might support only a handful. This meant larger populations, more workers, more inventors, more of everything. When agricultural societies met hunter-gatherers, the farmers usually won through sheer numbers. Over thousands of years, agriculture spread across the world where the climate allowed. Sometimes, farming peoples migrated, displacing or absorbing hunter-gatherers. Other times, hunter-gatherers adopted farming from their neighbors. Most humans transitioned from mobile hunting and gathering to settled farming, setting the stage for complex civilizations. Permanent settlements grew into cities. Cities needed food from surrounding farms, leading to trade networks. Trade required record-keeping, which led to the invention of writing in multiple regions. Complex societies developed hierarchies with rulers, priests, craftspeople, farmers, and slaves forming different social classes. Organized religion became more prominent, with temples and pyramids built to honor gods or rulers. Specialization emerged as people focused full-time on pottery, metalworking, weaving, or administration. The first civilizations arose in river valleys where agriculture was particularly productive: Mesopotamia, Egypt, the Indus Valley, and the Yellow River. These civilizations developed writing, mathematics, astronomy, and metallurgy. All of this happened within just a few thousand years after the Ice Age ended. It's an incredibly rapid transformation. But it's also important to remember that even as these civilizations rose, hunter-gatherer societies continued to thrive in other parts of the world. Australia's Aboriginal peoples maintained their hunter-gatherer lifestyles for tens of thousands of years after agriculture was invented elsewhere. In the Americas, many groups remained hunter-gatherers even as others developed agriculture and built cities. In Africa, groups like the Sand People hunted and gathered successfully, until very recently. Agriculture wasn't inevitable or universally adopted. It was one strategy among many. The ecological consequences of this transition were profound. It wasn't just about the extinction of megafauna. Forests expanded dramatically, changing countless ecosystems. Species adapted to open grasslands had to move, adapt, or go extinct. Cold-adapted species retreated northward or to higher elevations, while warm-adapted species expanded their ranges. The distribution of species across the planet shifted massively, and humans were increasingly shaping these ecosystems, often in ways we didn't fully understand until recently. Indigenous peoples around the world used fire as a landscape management tool, burning regularly to maintain open areas that attracted game animals or promoted the growth of useful plants. This burning had huge effects on vegetation patterns. What we think of as natural, pristine ecosystems are often actually anthropogenic, shaped by thousands of years of human fire management. In Australia, Aboriginal burning transformed large areas from dense forest to open woodland and grassland. In North America, Native American burning maintained vast prairies and savannas that might otherwise have been forested. When Europeans arrived and disrupted these burning practices, ecosystems often shifted dramatically. Forests grew where they hadn't been for millennia. Fire-adapted species declined, while fire-sensitive species increased. The wilderness Europeans saw wasn't pristine nature. It was often the result of thousands of years of active human management. The extinction of megafauna also had cascading ecological effects that we are still trying to fully understand. Mega herbivores like mammoths weren't just eating plants, they were ecosystem engineers. They knocked down trees, maintained open areas, distributed nutrients through their dung, and created trails and wallows. When they disappeared, these functions disappeared too. Some scientists believe that forests expanded after the Ice Age, partly because there were no longer giant herbivores suppressing tree growth. There's even a hypothesis that megafauna extinction contributed to climate change. Large herbivores produce a lot of methane, a potent greenhouse gas. When megafauna populations crashed, methane emissions might have decreased significantly, and the transformation from open grasslands to forests changed the reflectivity of the land surface, affecting how much solar energy was absorbed versus reflected. The loss of the megafauna, it wasn't just the loss of food for early humans. It was the loss of materials. Mammoth ivory for tools, for art, for building, hides for clothing and shelter, bones for everything from needles to the frameworks of dwellings. I often wonder how profoundly that disappearance forced people to adapt, driving technological innovations. In a way, the extinction of the megafauna might have actually sped up the transition to agriculture in some regions. If your primary food source vanishes and you can't find a good replacement by hunting smaller animals, you either starve or you find a new way to survive. Agriculture became that strategy. It's almost paradoxical. The extinctions that ended the Ice Age world might have inadvertently pushed humans toward lifestyles that would ultimately create modern civilization. The Holocene, the time since the last ice age, has been unusually stable compared to the climate swings of the Pleistocene. There have been variations, of course, warm periods and cold periods, droughts and floods, but nothing like the dramatic swings of the Ice Age, with its rapid warming and cooling events. That stability, I believe, is what allowed civilizations to develop. It's difficult to build cities and plan agriculture when the climate might flip dramatically within a single generation. But the Holocene stability allowed humans to make long-term plans and investments, building irrigation systems and monumental architecture that took decades or even centuries to complete. Different parts of the world experienced the Holocene differently. The Sahara Desert, now a vast, empty wasteland, was actually green and wet during the early Holocene. From about 11,000 to 5,000 years ago, increased monsoon activity brought more rain to North Africa. Rivers flowed through what is now desert. Lakes filled valleys. Vegetation covered areas that are now bare sand. People lived throughout the region, herding cattle and developing agriculture. Rock art from this period shows hippos, giraffes, elephants, animals that now seem impossibly out of place there. But then, around 5,000 years ago, the African monsoons weakened and the Sahara dried out relatively rapidly. Within just a few centuries, the Green Sahara became the desert we know today. This desertification forced populations to migrate, many moving to the Nile Valley, where water remained available. Some historians believe this migration and concentration along the Nile contributed to the development of ancient Egyptian civilization. Climate change, driving human migration, driving civilization development, all interconnected. Similar stories played out elsewhere. The Middle East was relatively wet in the early Holocene, supporting agriculture and early civilizations. But droughts have repeatedly stressed or collapsed civilizations there. In Mesoamerica, droughts have been linked to the collapse of Maya civilization. In the American Southwest, extended droughts forced the abandonment of settlements like Mesa Verde. Climate variability during the Holocene has been a constant factor shaping human history, even though the swings were mild compared to the Ice Age. And here we are now, roughly 11,700 years into the current interglacial period. Based on past interglacials, we should eventually slide back into glacial conditions at some point. Different models offer different predictions. Some suggest we have thousands of years before the next glaciation begins. Others think tens of thousands of years. The orbital cycles are complex, and their effects don't always line up predictably. But there's a massive wild card now: human activity. We are affecting global climate on a scale that might override the natural cycles entirely. We've increased atmospheric carbon dioxide from the natural interglacial level of about 280 parts per million to over 420 parts per million. That's a 50% increase in just a couple of centuries. The ice core records going back 800,000 years show nothing like this. We're in completely uncharted territory. And this brings us to the big question: what happens next? So, here's where things get really interesting and honestly a bit scary. We've spent this whole time talking about how the 100,000-year cycle has controlled Earth's climate for millions of years, creating ice ages and shaping the evolution of life, including humans. But now, for the first time in the history of this cycle, one species has the power to override it, and that species is us. Some scientists think we've already delayed or canceled the next glaciation. The extra carbon dioxide we've pumped into the atmosphere warming the planet, making it unlikely that Northern Hemisphere summers will be cool enough to allow ice sheet formation even when the orbital cycles shift toward glacial conditions. We might have prevented the next ice age from ever happening. Sounds good, right? Nobody wants kilometers of ice covering Canada and Scandinavia again. But the problem is, we're not just preventing the next ice age. We're warming the planet way beyond normal interglacial conditions. And we're doing it incredibly fast. Let's talk about what we've learned from studying ice age cycles and why it matters right now. First, and most importantly, the climate system has tipping points. It's not linear or gradual. You can push the system for a while and see only small changes, then suddenly cross a threshold, and boom, rapid dramatic shifts happen. The Younger Dryas is the perfect example. Gradual warming, then catastrophic freshwater flooding, then abrupt climate reversal within decades. The system flipped states faster than human lifetimes. We're seeing similar threshold behavior today in multiple parts of the climate. Ice sheets don't melt in a way that's uniform or predictable. I've learned that they can remain stable for very long stretches, and then suddenly, almost without warning, accelerate their melting when they reach certain critical points. It reminds me of trying to hold back a dam that's about to burst. We're pushing multiple systems toward their tipping points simultaneously. Arctic sea ice is declining dramatically. The minimum extent in summer has dropped about 40% since satellite measurements began in the 1970s. Some models even suggest the possibility of ice-free Arctic summers within just a few decades, and I always come back to those feedback loops. Ice reflects sunlight, but ocean water absorbs it. Less ice means more heat absorption, which of course means more warming and even more ice loss. It's self-reinforcing. The Greenland ice sheet is losing mass at an accelerating rate, around 250 billion tons per year, according to recent measurements. Greenland contains enough ice to raise global sea levels by about 7 meters, if it all melted. No one expects it all to melt soon, but even losing a fraction of it over the coming centuries would massively impact coastlines worldwide. And once major melting starts, feedback effects make it hard to stop. Exposed, darker rock absorbs more heat. Meltwater lubricates the ice base, making it flow faster. Warm ocean water gets underneath and melts from below, all positive feedbacks amplifying the initial change. The West Antarctic ice sheet is particularly concerning because much of it sits on bedrock below sea level. Warm ocean water is already getting underneath it, causing melting. Some scientists believe that major portions might be committed to collapse over the coming centuries, even if we stopped warming today. If that happens, we're looking at 3 to 5 meters of sea level rise. That would remake coastlines globally and displace hundreds of millions of people. The carbon cycle is being disrupted in ways that mirror the Ice Age cycles, but in reverse and much faster. During glacial periods, carbon dioxide dropped to around 180 to 200 parts per million. During interglacials, it rose to about 280 to 300 parts per million. This roughly 100 parts per million swing took tens of thousands of years, driven by natural ocean and vegetation processes. We've increased carbon dioxide by over 140 parts per million in just over a century. We're replicating the natural cycle's entire range in a tiny fraction of the time. And we're blowing past natural interglacial levels into territory Earth hasn't seen for millions of years. The last time carbon dioxide was this high was probably the Pliocene, around 3 million years ago. Back then, temperatures were several degrees warmer than today. Sea levels were 15 to 25 meters higher, and the Arctic was forested instead of ice-covered. That's where we're headed if we don't change course. And the rate matters as much as the magnitude. Ecosystems can adapt to gradual changes over thousands of years. Species migrate. Evolution selects for new traits. Ecological communities reassemble. But when change happens in decades or centuries, there's no time for gradual adaptation. Species either move fast enough or they go extinct. We're already seeing range shifts in thousands of species. Plants flowering earlier, animals moving toward poles or up mountains, ocean species shifting to cooler waters. Some species are adapting successfully, others aren't. And we're likely headed for another extinction wave. Maybe not as dramatic as the megafauna extinctions, but significant. Current extinction rates are already elevated above background, and climate change is adding another major stressor on top of habitat loss and pollution. Here's something that keeps scientists up at night. During Ice Age cycles, carbon dioxide changes were a feedback, not a forcing. Orbital variations changed sunlight distribution. This affected temperature. Temperature changes affected ocean chemistry and vegetation, which changed atmospheric carbon dioxide. Carbon dioxide then amplified the temperature changes. It was a feedback loop within the system responding to external astronomical forcing. But what we're doing is different. We're directly forcing carbon dioxide changes by burning fossil fuels. This is direct forcing, not feedback. And all those natural feedbacks that amplified carbon dioxide changes during Ice Age cycles, they're still operating. They're amplifying the changes we're causing. We're pushing on a system with built-in amplifiers, and we don't fully understand all of them or where the thresholds are. Permafrost is a huge wild card. There's around 1,500 billion tons of organic carbon stored in frozen Arctic soils. That's roughly twice as much carbon as currently in the atmosphere. As the Arctic warms, permafrost thaws and microbes start decomposing that organic matter, releasing carbon dioxide and methane. Classic feedback. Warming causes thawing. Thawing releases greenhouse gases. Greenhouse gases cause more warming. How fast this happens is uncertain, but the potential for permafrost to become a major additional carbon source is real and scary. The ocean has absorbed about 90% of the extra heat trapped by greenhouse gases so far, which has slowed atmospheric warming, but at the cost of warming the ocean itself. Warm water holds less dissolved oxygen. We're already seeing expanding dead zones where oxygen has dropped too low to support most life. Marine organisms are stressed by warming, acidification from dissolved carbon dioxide, and oxygen loss simultaneously. Coral reefs are being devastated by repeated bleaching events. These ecosystems that support enormous biodiversity are collapsing. I find myself thinking about future geologists, millions of years from now, sifting through the sediments of our time. What will they see? They'll find isotope ratios reflecting massive carbon combustion, extinction signatures, and the strange novelties of our age, plastics and concrete embedded in the earth. They'll recognize that something unprecedented happened during this brief moment in Earth's history. Whether they'll also find evidence that we successfully navigated the crisis, that remains to be seen, doesn't it? The answer hinges on what we do in the coming decades. The Atlantic Meridional Overturning Circulation, or AMO, shows signs of weakening. The data is noisy, and it doesn't stretch back very far, but several lines of evidence suggest it might be slowing. If it weakens significantly or even shuts down, it could cause regional cooling in parts of Europe. A paradox, global warming leading to regional cooling. It happened during the Younger Dryas, and it's a stark reminder that climate is complicated, often counterintuitive. What do we do with this knowledge? The 100,000-year cycle teaches us a crucial lesson. Earth's climate is remarkably sensitive to even small changes. The orbital variations that trigger ice ages are tiny shifts in seasonal sunlight distribution. Yet, combined with feedback loops, they're enough to tip the system from one state to another. We're applying a forcing that is much larger and faster than those orbital variations. The response will be substantial. The only questions are how substantial and on what time scale. Climate has momentum. Ice sheets take thousands of years to grow, but they can collapse much faster. Once major melting begins, stopping it becomes incredibly difficult. Ocean circulation changes can be hard to reverse. Some of the changes we're causing are essentially irreversible on human timescales. Even if we stopped all emissions tomorrow, temperatures would remain elevated for centuries as the ocean and atmosphere slowly reach a new equilibrium. Sea level would continue rising for centuries, perhaps millennia, as ice sheets respond to the warming already in the pipeline. It's uncomfortable to confront. We've likely already committed to significant changes, even with aggressive emission reductions. Some warming, some sea level rise, some ecosystem disruption is already baked in. The critical question is how much more we add. Every bit of additional warming makes things worse. Every tenth of a degree matters when dealing with systems teetering on tipping points. The paleoclimate record is clear. Rapid climate change is incredibly hard on societies. Climate shifts at the end of the Ice Age contributed to megafauna extinctions and forced major changes in human subsistence. Droughts during the Holocene toppled civilizations. Those were natural variations over which societies had no control. We're causing changes faster and potentially larger than those natural variations. With over 8 billion people to feed and house, many in areas vulnerable to climate change, the implications are staggering. Coastal cities face flooding from sea level rise. Agricultural regions face shifting rainfall and more extreme weather. Water resources are stressed by changing precipitation and glacial melt. Tropical regions could see temperatures exceeding human survivability thresholds for outdoor work during heat waves. Island nations could literally disappear. The humanitarian implications are enormous, and they're unequally distributed. Those who contributed the least to causing climate change are often the most vulnerable to its effects. Understanding the problem is the first step toward addressing it. We know more about climate now than ever before. We can see changes happening in real time with satellites and monitoring systems. We can model future scenarios with increasing accuracy. And we have technologies available that could dramatically reduce emissions if deployed at scale. Solar and wind are now cost competitive with fossil fuels in many places. Electric vehicles are becoming mainstream. Energy storage is improving. Carbon capture is being developed, though it's not yet proven at the necessary scale. The challenge isn't really technological anymore. It's political, economic, and social. Getting 8 billion people to coordinate on emission reductions, equitably distributing costs and benefits, navigating competing interests, that's the hard part. Climate change is the ultimate tragedy of the commons. Individual actors benefit from burning fossil fuels, but everyone suffers the consequences. Solving it requires collective action on a scale humanity has never achieved. I know some people feel despair. The problem seems too big, changes too slow, obstacles too numerous. I understand that feeling. But humans have navigated existential challenges before. We survived the Ice Age through adaptation and innovation. We transitioned from hunting megafauna to agriculture, fundamentally transforming our relationship with the planet. We've overcome diseases, expanded lifespans, created technologies that would seem like magic to our ancestors. We're not helpless. We're just facing a problem requiring unprecedented coordination. The 100,000-year cycle will eventually resume, assuming we don't permanently alter it. The orbital mechanics haven't changed. Naturally, Earth would eventually slide back into glacial conditions tens of thousands of years from now. But we're writing a new chapter, one where human activity is a major climate driver, not just a responder. We're affecting the planet on a scale comparable to the astronomical forces that controlled climate for millions of years. No species has ever had this influence. It's both inspiring and terrifying. The cycle reminds us that climate is dynamic, sensitive to forcing, full of feedbacks and tipping points. It's not a stable, unchanging background. It's an active system responding to inputs. For millions of years, those inputs were natural. Now we're adding a new input, and the system is responding. We are living through a moment unlike any other in Earth's 4.5 billion years. I find it almost unbelievable that a single species, us, understands the global climate system while simultaneously altering it. We possess knowledge and power no organism has ever held before. What we choose to do with that knowledge will determine Earth's trajectory for thousands, even millions of years. The Ice Age cycles have shown us just how resilient life can be. Earth has endured dramatic climate shifts, and life has not only survived but adapted and thrived. Life even survived the asteroid that wiped out the dinosaurs. It will survive this too. The real question is whether human civilization as we know it will thrive, or whether we will face massive disruptions that could have been avoided with foresight and decisive action. I began by discussing the mystery of the 100,000-year cycle and how scientists patiently unraveled it. Now, that same scientific community is warning us about anthropogenic climate change, using the very same methods that revealed the Ice Age cycles to begin with. If we trust the science that explained the past, shouldn't we also trust its predictions for the future? It's becoming increasingly clear that we're pushing the system incredibly hard. We will see significant responses, and the window for avoiding the worst possible outcomes is rapidly closing. The Ice Age taught our ancestors to be adaptable and innovative. That resilience is in our very DNA. We can harness those traits to navigate the challenge we've created, but it requires collective and swift action. The climate system has momentum and inherent time lags. Actions taken today won't fully manifest for decades, but inaction today commits us to changes that will unfold for centuries to come. Every year of delay only makes the eventual response harder and more disruptive. So, where does that leave us? We're 11,000 to 700 years into an interglacial period that should eventually come to an end. We are armed with an understanding of how climate works, yet we are actively changing it faster than natural processes typically do. The 100,000-year cycle that shaped human evolution is now being overridden by human activity. We've become a geological force. The only remaining question is whether we will wield that power wisely or recklessly. The answer will determine what kind of planet future generations inherit and whether they'll view us as ancestors who rose to the challenge or as a cautionary tale of a species that understood the problem but ultimately failed to act. The clock is ticking. The cycle that sustained life for millions of years is still operating in the background. But for the first time, it might not matter. For the first time, one of the species it created has the power to override it. What we do with that power in the next few decades will determine not only our future, but also the future of countless other species sharing this planet with us. The Ice Age is over. The question now is, what comes next? Unlike our ancestors, who simply had to survive the cycle, we have the power to shape it. It's both an incredible responsibility and an incredible opportunity. It's time to see what we do with it.